Yeah. That's not very much. No, I know. Well, you've been here for the introduction. I was. Yeah. But what we're
Slava.
the offspring of people and we are currently working on a systematic so what is it?
Okay, so probably can.
Wait, to the microphone here, no? Huh? Do we need a microphone?
Oh, here's the microphone.
Yes. So we have to finish it for
Sorry about that.
Sorry, Christoph.
Okay, so today we have the fourth lecture from Slava, and today Slava is going to talk about some instructional sequences based on the human cognitive architecture.
Today we change.
Oh, the problem solving, learning instruction. Okay. The microphones.
Do we need a microphone here?
I'm not sure. Maybe not. No, we don't need it, right? Okay. Yeah, just it's less problems. Okay. All right. Okay. So again. My gratitude to Leverhulme Trust, of course, for finding this trip and making this possible. Today's the lecture 4.
No, I jumped off the slideshow, so F5.
F5, no.
Okay, the window is not active. Click the window, just anywhere. No.
Yeah.
No. Okay.
Yeah. Good, thanks. Yeah, so the lecture 4, we're going to talk about problem solving in learning and instruction generally. So just to give some overview, some topics that I want to cover in this lecture. It's firstly, it's not the exact sequence, but more like topics that will be covered, because some of those will focus on different times and get back probably again. So firstly, some evolutionary perspective view from point of view of those 5 principles that we discussed before. Then I need also to cover this topic of problem solving as an instructional method. So how we can, how we can learn from problem solving, and the final topic is general expert problem solving, how expert problem solving do problem solving, and what instructional implications from that. So to start the first one, evolutionary perspective, just to remind you, those in the lectures 1 to 3, first 3 lectures, we discussed we discussed all of them in some degree of those principles, but specifically we covered that so-called information store principle. That, again, I remind you, that was principles of so-called natural information processing systems, including human cognitive architecture. Therefore, we apply it to human cognitive architecture. So information store system with stating that any of those natural information processing system has huge information store. That essentially one, if not most important part of that system. In human case, it's long-term memory. So we discuss long-term memory to some details, characteristics, and form of knowledge in long-term memory, in form how its knowledge is stored there, in form of schemas and so on. So we covered that topic, long-term memory. Then we discussed working memory, which is essentially implementation or the form of implementation of this so-called narrow limits of change principle, which actually stipulates that when a system operates in novel environment, then it's allow only very small, some incremental changes to that information store. Otherwise, it could damage its operation, damage its functionality if the big changes. So in human cognitive architecture, working memory essentially performs this role. That's one of the roles of working memory from evolutionary perspective. And we discussed characteristic of working memory. In relation to that, we discussed some introduction to cognitive load theory, which essentially is a theory that studies these instructional implications of working memory limitation and tries to devise some instructional means to getting around those limitations. So we covered that. Then finally, we covered this principle with so-called environmental organizing and linking principle. But in short, it stipulates that if the system operates in familiar environment, in other words, it means that the system has sufficient information patterns in that information store that allowed it actually to function in that external environment, then those limitations that we talk about in the second principle, that's not really relevant, because the system in this case have the capacity to overcome those limitations. And in human cognitive architecture, then we discuss, so when we have some sufficient knowledge base in long-term memory in specific area, in other words, if we are expert in that area, we are able to get around those working memory limitations. Just simple, that principle, that chunking that we discussed to some degree, that actually shows how that is done in human cognitive architecture. So the topic of expertise and how that expertise affects this kind of information processing. So we discussed that one essentially the last lecture 3 was about that. So up to now, we covered these 3 principles from evolutionary perspective and discussed in relation to that these 3 topic of long-term memory, working memory, and expertise. So today, we have 2 more principles to talk about. One is so-called Borrowing reorganizing principles, which says those remaining 2 principles essentially is about how information processing system get knowledge or get information pattern into that information store, which means they're used for doing this. So one of those means is described by this principle, borrowing and reorganizing, is actually they are borrowing it from other systems or from other sources. So in human cognitive architecture, we were borrowing from other people, we're reading, we're listening, we're imitating. It's a lot of ways, but we're borrowing essentially, but not just copying it literally. We reorganize it in connection with what is already in our long-term memory. So we do this kind of integration. So it's never just direct copying. None of that copying really exists. In nature, we always kind of reorganize, we fit it into what is already in long-term memory. But we will talk about this principle in more detail next lecture, in lecture 5. That would be essentially about this. Because in human cognitive architecture, when we're talking about, especially from instructional implications, that the issue of direct instruction, that the issue of work examples from cognitive load theory perspective. So we're going to talk about it next week. Today we talk about problem solving. the problem solving is essentially things that covered by this principle, the randomness as genesis principle, has this kind of a to some degree a kind of biblical name, the randomness as genesis, but essentially his principle is that any new information that which couldn't be borrowed, of course, there is something that could not be. We have to guess in the first place some information if it doesn't exist. So we get in somehow we have to get new information, any system, because not everything exists to be borrowed. And how any new information could be get? So we gone into this principle. It could be get also by some random so-called generate and test procedure. So we randomly try different possible solutions, different possible outcomes, and see if they fit the task. If they do the task, then we adopt those solutions. So we accept them. The system actually adopts them. If not, we reject them and do some and try another one. So essentially, this is kind of this random generate and test search processes that natural information processing system use to get new information that could not be actually borrowed. So problem solving in human case is essentially way of realizing or implementing this principle in human cognition. So we will look at problem solving from this perspective. So in this case, what we need to discuss generally in this lecture to cover this issue of problem solving in human cognition in learning and instruction as well to some degree of completeness is firstly we need to look at this as actually the mean of generating new knowledge in the absence of any of relevant knowledge in long-term memory. So if we face in a situation in life that we cannot solve or we cannot perform effectively because we don't have simply knowledge to do that. So we face in this situation, we have to discover this way of dealing with this problem. So we're facing some new problem for which we don't have schemas to apply to solve it, and we have to generate this knowledge from the scratch, if you like. So that one thing that we need to discuss today, these functions of problem solving as a way of generating new knowledge. So yeah, we're doing random search to get it, generate and test. This is a little bit idealistic view, of course, because ideally it says that it's completely random. It's kind of the random search. We just randomly try possible ways and then try if they fit the task, the goal or not, and reject or adopt them. Of course, in reality, nothing is completely random, because even when we do some random search, we still do some kind of reasoning. We do some the next if we select some next move to randomly search, we don't select it completely randomly. We already having at least some knowledge what happened with previous move, and we do the next one already kind of with some sort of direction. And we will see it in trial and error or mean sense analysis that we'll discuss shortly. So we will see how that actually happening. So the next issue that we need to discuss to cover this problem solving human cognition, how we solve problem when we have some knowledge to do that. So meaning that using available knowledge to solve problem. And here we again get into that issue of expert problem solving, because if we have some knowledge in some specific task area, we can say that we are sort of expert in this task area, and we approach the problem like experts. So what that mean, and what the specific of that approach. So that's kind of different aspect. So one is generating new knowledge by random search, and another using knowledge to solve it in expert-like term. So that two aspects of problem solving in human cognition. When we're talking about problem solving and learning, or learning and instruction, this aspect of the topic. So again, there is a couple of things that we need to discuss. Firstly, how we learn to solve problems, how best to learn or to teach problem solving. So how should students be instructed in problem solving skills in a best possible way? For example, do we need them to teach some generic problem solving skills, some of those heuristics that could possibly they would apply anywhere in a workplace and would be ready to workplace, or anything is kind of any problem solving skill is domain specific, so we need to teach only some very specific procedures they need to perform in specific task area. So this type of questions, again, we need to pay attention to discuss in this topic. And another aspect of this problem solving and learning is solving problem to learn, or in other words, problem solving as an instructional tool, as learning tool. Would just getting practice, a lot of practice in problem solving would maybe solve the question of teaching to solve problems or not. That sort of another aspect that we need to talk about. So two aspects of problem solving in cognition generally, and two aspects problem solving in and learning and instructions. So that's pretty much what we're gonna talk about today in some way, and into some degree of details. So again, is an important issue in all of that, as you notice, was knowledge in problem solving. We discussed that, do we have knowledge or not? If we have knowledge, we do one way with the problem solving, and we don't have knowledge, we do the other ways, like this kind of random generation. So knowledge is important, critical thing here. So what type of knowledge generally we can use in problem solving? One is obviously domain-specific knowledge, what we call domain-specific knowledge. This is a knowledge in particular field of study, or whatever the field is, or even getting more down to the specific topic or specific task area within those specific fields. So that is domain-specific. Of course, that go down to specific procedures, specific principles, specific facts, and so on in specific domain. Declarative, procedural knowledge we discussed. On the other side, within a domain-specific knowledge, we can talk not only about specific domain, but also general domain. So there is some kind of this categorization, subcategories within domain-specific. We can specify really specific domain knowledge, which is, for example, how to solve linear algebra equation. That's a specific domain knowledge. We have specific procedure, how to solve this quadratic equation. We have formula. That's specific domain knowledge. On the other side, there exists some kind of general domain knowledge as well. It's still domain knowledge. It's still domain specific, but it's general domain specific, like some principles, like those Newtonian principles in physics. That's domain specific because it's physics. It's not applied in chemistry. It's not could be applied in history or any other area, but it's still to significant degree general. It could apply to different task areas in physics and so on, or some other principle in other domains. So this kind of categorization as well. It's maybe not that important to today's discussion in general, but it's important to some other issue like issue transfer within the broader domain. Then that general domain knowledge plays a critical role in a transfer because those principles they are transferable to different specific tasks in the domain. Because if we are limited just specific procedures, specific formulas or specific facts, they might not transfer to even another task area already. But general domain knowledge is more transferable. But we're not going to talk about transfer much today, but this distinction might have some importance for that. So that kind of domain-specific knowledge. On the other side is domain general knowledge or general knowledge, which is a knowledge that applies to all domains, throughout all domains, not limited to one domain. So it's some kind of general search procedures, for example, how we generally search. And to some degree, that knowledge, there's some kind of arguments in theory that is much of that really actually even biologically primary in nature, because that's something that we are evolved to use and apply. We search for solution using these random attempts. The small children actually do that. They use this heuristic, essentially the trial and error, if you like, or some example of the even more relatively complex heuristics like mean sense analysis. We're going to talk about that just shortly. The small children use it without any instruction. So much of those is a biologically primary by nature that doesn't need any instruction in a way. But generally speaking about general knowledge or domain general, and not linking, of course, to a specific domain. And often it's just related to that kind of structuring the general approach, or also related to some metacognitive processes. So this general knowledge. I will talk about this general knowledge to some degree of more details now, and we start actually not from domain specific, but from that domain general, just to finish with that. So one significant part of that domain general knowledge is general problem solving models. So how people generally approach problem solving. There is some different type of models, but most of them really could be summarized in those 5 steps. So firstly, we need to identify problem. Then we possibly need to represent it somehow. Then we need to select a strategy to deal with this problem, including some specific procedure or whatever is available. Then we need to implement this strategy to do actually this problem solving. And finally, we need to evaluate the solution to look back how that was and to learn something from this. One of the example of these general problem solving models in mathematics was very popular at some stage, and popular and actually still popular. It's this George Poyer's model of problem solving in mathematics. That's a book, How to Solve It, firstly published in 1945 and then republished many times in different kind of second and following editions. Just to, again, it's pretty much repeats those 5 steps that I described on previous screen. Again, firstly, need to understand the problem and a representation actually within that as well. So it not have representing the problem in separate step. So understanding the problem involves that. But the most important one is called devising the plan. To devise a plan, you need to select that strategy essentially. I'll just show you several, not all, but selectively, several specific techniques that suggested within this devising and plan step. So for example, like one of that, guess and check. Guess and check. Some random trial, if you like. Guess some random and check if it's performed or not. On the other side, it's like solve an equation. That's something that's pretty specific, right? You need to know specific procedure how to solve an equation. To guess and check, you might not, but probably you still need something to of that nature. But solve the equation, you need specific procedure. Walk backwards. Another suggestion. What would that mean? Walking backwards from the problem goal. That would be mean sense analysis that we're going to talk about in a few minutes. This is a kind of general heuristics. It's a general. It's not specific. It's domain general knowledge. So the first one, guess and check, is domain general technique. Second one is pretty much specific. Next one is walk backward in domain general. Use a formula. Another suggestion and technique is a specific. You need to know the formula to use it. It's a general. It's a specific procedure. And the final is like, not the final, but just one of those listed, the possible technique, be creative. That probably most general and to that degree in as well as useless suggestions to be creative in generally. And the next two steps is the carrying out the plan, of course, and looking back, evaluating. So pretty much the same step. Why I mentioned this book here and this model of problem solving, not only because it's in mathematics, and this is a mathematics department, and some of you may be even familiar with this book. And many people regard it as a very, very good things to read by anyone. I probably agree with that. It's good things to read, but I have some personal experience. That book was published, you see it in those years, and I was in the year 6, 7 in a high school in about 1968. And I was kind of mathematics competition enthusiast. I participated in many of those mathematics Olympiad throughout. At that time I lived in Soviet Union, and those mathematics Olympiads very, very popular and was very well organized actually in that country at that time. For all country was different levels, from the level of school, region, republic, and then the whole union competitions level. So it was like sports. I was got involved in this very well in mathematics area. So and I was about in year 6 or 7 at that time, and mother of my friend, she worked like librarian, and the book come to the library, and she picked it up for her son, who also was kind of a enthusiast in this area as well. And we look at that book, and we were so enthusiastic when reading that introduction and everything, that we saw that now we have solved treasure. We will read this book and we will be able to solve any problem, and we will be able to win any competition, and that will solve all our sort of problem, all our expectations and everything. And then we started reading it and reading it and reading it, and in the end, essentially that was the biggest disappointment probably in my life, maybe not the biggest one, but one of those. And because essentially we learn not much really. In order to solve those problems and win competition, you need to have more effective, could be some other means. Maybe that book was, of course, useful for some understanding, for some scheduling, some general approach, but not to solving specific problems. What taught me at that time to solve specific problems and win those competition to the significant level was just studying a lot of specific example of how people solve the problem. And again, in that country at that time, it was a whole industry actually in mathematics education and physics to some degree as well. The university professors were involved a lot into actually writing for students how to solve problems in specific domains, not how to solve problems in terms of this book, but how to solve specific problems in specific area, and provided a lot of those specific example and technique and method of solving specific problem in specific type domains. Specifically, books addressed high school and secondary school students, not the university students. It was all written by university professors in many cases. So I read a lot of those, and they covered the problem-solving method in very different area of mathematics. So and that significantly helped me. So studying those examples of solution, that was something that really I found much more helpful than studying this or learning these general, so-called general problem-solving models. When we're talking about selecting this appropriate strategy in this model, that essentially is the most important stuff and most important step in this model, because that's where you have to select your specific solution procedure. So for this, either you need to know this specific solution procedure or algorithm, as we can say. So, or you need to apply some general problem solving method if you don't know this specific solution procedure that could possibly allow you to help you to structure at least approach. So studying those algorithms, which essentially are procedural schema that give you the specific solution steps, they're probably most effective way to approach a problem. If you know a lot of those algorithms in different areas, or a lot of those procedural schemas in different task domains, you will be able to solve the task in those specific domains very well. So they are kind of guaranteed to work. But of course, you might not know any of that kind of algorithm or schema yet, or they might not exist if we're talking about some real kind of big problem. So you have to. So in this case, what could be happen then? Those heuristics they possibly could work to some degree to structure your approach. This kind of this rule of thumb, if you like. We look at some of those shortly, but they obviously don't guarantee a solution. They don't have any degree of kind of effectiveness. They can just help you to structure possibly approach to the problem, but no way they give you the solution. That's what happened with that sort of move. They have helped to structure some general approach, but never really help to solve the specific problems. So let's look at those firstly, briefly, algorithms. That we're talking essentially about those procedural schemas. If you have it, you know how to apply it, you apply it and you solve the problem fast. So again, I'm using this algebra example all the time for illustrating different topics. So if you need to solve this equation and you know the schema, you come up with solution right away. Like probably most of you do that. But if you even don't know that kind of automated, well-learned schema, but you know the general procedure in a way, you can do this kind of step by step to do some intermediate step, divide by 5 by both parts, and then come up with that. So, but that means that you know algorithm, you know the schema, and you apply in the schema either an automatic or with some sort of reasoning, but you do that quickly and effectively. If you don't know, then if you don't know the schema, then you need to apply some of that, possibly some of those heuristics, which is most usable, most popular, this kind of trial and error, of course. You just try different possible substitute for X in that case. In this case, they're taken from some specific student during one of our studies. So as you see, students was finally able to solve it in all cases correctly, but it's not really an efficient way to solve problems, because why it's not efficient way we will discuss a little bit later. But from it requires firstly, as you see, a lot of effort that in a way unnecessary if you know something, if you know algorithm, of course. But essentially that could be effective but not efficient. Effective in a way that you will be able to solve, possibly not. But it doesn't guarantee, but you can try. But the trial, of course, that's the example of this randomness, if you like, random generate and test. But it's not completely random again, because every next step or trial that you do, it based on the result of the previous unsuccessful one. So you're trying to get closer to that area where that sort of where that 5x would get you closer to -4. So you don't randomly select those x completely. You select them with some kind of with some goal in mind. So it's a random, generate and test, but not completely random. Some experience or some knowledge even with this narrow kind of task here, even help you to could helpful in this case. So another important heuristics is this means-ends analysis, which is essentially considered as a general problem solving for people. That how we able and that computer modeling of human problem solving to a significant degree was based by studies of and Allen and Simon. The modeling of human problem solving based on this mean-sense analysis. So what is mean-sense analysis is when you have some problem goal, you select some sub-goals that get you possibly to that goal. You try to get some sub-goals that get you closer to the desired final goal, that reduce the distance with your current state and that goal state that you want to achieve. So you find in the moves and sub-goals that gradually will reduce that distance between the current state and the final goal. So again, it's not to some degree it is implementation of that randomness, but it's not a complete random as well, because you select those sub-goals not randomly. You select it from some point with some kind of reasoning. You're trying to get this distance shorter. So in this case, you're walking kind of backward from the goal, go back where your current state is, but trying to reduce the distance. So just to illustrate it, the simplest illustration of this mean-sense analysis would be, of course, like in everyday life. If you need to get from London to School of Mathematics or wherever in Loughborough University, you just reasoning, okay, if I get to the Loughborough train station, then I will know what to do. I will take the bus and get to the Loughborough University. So the sub-goal becoming getting to that Loughborough train station. Okay, so that's how you select those sub-goals, getting you closer. If you're talking about yeah, that's Newell and Simon, the very seminal book that actually to significant degree describes this method as a general problem-solving method. So if in case of this geometry problem, we still have goal, find value of angle x in these kind of conditions, in this environment, right? So doing this, applying this mean-sense analysis would mean that we just reasoning in this case. If we know the value of y, angle y, then we will do the job because those angles are equal. So sub-goal became in this case finding this angle y. So we know some mathematical facts here that some of those angles in triangle, they add to 180 degrees. We can use this to find that value of y. So, but sub-goal becomes this finding this angle of z. If we find angle z, then we will find angle y by using this this theorem. So finding z becomes some goal. So eventually we know them another facts that the angles add to 180 degrees, and that's how we can find z. And then we're retracing it all backward to the y and then finally to the x. So that's how is briefly how it works in specific problem, mean-sense analysis. So we're walking backward essentially from the goal all the way backward to the situation when we can answer to find sub-goal, and then we retrace. Okay, I show this picture not just generally because most or many of you probably are quite familiar with that and generally mean-sense analysis, but to illustrate some facts that we will need to answer a little bit later in this lecture. Why is this method, or is it instructionally effective or not? Could it be effective as a means of instruction using that mean-sense analysis? And having this now explained and shown how that looks like mean-sense analysis, we can answer that questions a little bit later. So, but that was kind of problem-solving situation when we don't have knowledge. If we have knowledge, then we are sort of kind of expert in the area. All right, how experts solve the problems, how they treat the problems. Here is some task taken from some well-known studies in expert performance. How you would categorize those in 3 groups? Any ideas?
Kings, Queens Revolution, 1789. So that's about the French Revolution. Then 1492, discovery sailors would be the second category.
Yeah,
About like,
we got you are expert in history. Yeah, that kind of how the expert would categorize. How the novices that have no idea about those historical facts would categorize. They put numbers in one group and then put words in other group and so on. Some probably kings and sailors and other soldiers, and on those surface kind of characteristics. But what the expert will do, that would be kind of surface characteristics. But what expert will do, they will do on their knowledge of actual events. In this case, the French Revolution, and another is Columbus discovery, right? So that would be how expert will do, because they have knowledge, their schemas, the knowledge of those those events. They would allow them to categorize it according to the deep structure. There's a lot of other studies was done in this kind of expert categorization. For example, in physics, the people were presented with those inclined planes task, like in physics, an object on inclined plane, and novices or some blocks or other things, and novices usually categorize them based on pictures. So those are inclined planes in one group, all these kind of blocks with some weight on another group, and so on. But some of those tasks could be solved based on one principles, physical, and other could be based on another principles. And the expert actually categorize them based on those principles that could be used to solve them, no matter what actually the diagrams look, the pictures look. So it's again, that's a general characteristic of expert approach to problem. So because experts have knowledge in that specific domain. So no general problem solving actually applicable here, models. Then you need to have knowledge of those principles in the domain, whatever the domain is, or most important kind of events in that domain. Is that some in that kind of more generic ways that would allow you to categorize them in this sort of deep sort of way and approach that problem solution based on those principles, how that's supposed to be done. So what the expert characteristics in problem solving in this case? Firstly, when they excel only in their specific domain, in those domains that are expert in, not in others and not in general cases. So secondly, and we talk about that last lecture when we talk about expertise, was a kind of difference. The expert actually process information in those chunks, if you like. Those chunks are those schemas, are those principles, if you like, in this case. Those chunks allow you to group information according to the way it's gonna be used for solving the task. So that's another. So they perform quickly with a few errors because they have that domain-specific schemas, domain-specific solution procedures. Because they experience those procedures many times, they have a lot of experience in a different number and a huge number of problems in their domain. We talked last lecture about this chess expertise, how much time that required to acquire this kind of expertise in chess, and a similar in other domain as expertise study shown. So experts actually recall those principles, those schemas, those chunks, if you like, and do the move. efficiently and without much of actual reasoning, because reasoning would be in this case that problem-solving search, that problem-solving search as an example of that randomness, random approach, random search. So if they don't have those knowledge, they would use that heuristics and random search to some degree of randomness with different degree of randomness. But if they are experts in the field or specific task domain, they will recall the solution schemas and apply them. And they'll do it quickly and efficiently. So expert, as you see, they do with problems on a deeper level. So they categorize based on those deep principles rather than some surface characteristic like it was in this demonstration. So of course they're able to hold more information in working memory and long-term memory. In working memory, because they have those chunks, they have the ability to chunk information in big groups. So they can increase this working memory capacity to essentially to unlimited capacity because due to that kind of chunks. And they have a huge knowledge base in long-term memory. So sometimes people talk actually like Erickson and Kinch in their sort of paper, which was actually called long-term working memory. So not working memory, not long-term memory, but long-term working memory as a kind of combination. This kind of virtual sort of reality, virtual memory, which is created specifically for the task, which includes some of those elements that in working memory currently, and also includes some of those schemas from long-term memories that have been activated. And they all together coming into this formation that is called long-term working memory. Some illustration for that from everyday life could be from reading like fiction sort of stories, reading novels. When you read that, we are expert in this everyday situation that normally covered in those fiction novels. So when you read a book, you can, and if you, for example, interrupt it on some page and go to the lunch, and then whatever 2 hours later you come back, go back to that page in that book, and normally you can continue reading from that point. You don't need to go back to the beginning of the book and reread what was there. You pretty much you're able to continue the reading the book from that point when you were disrupted a few hours ago. Because when you're reading that book, and we are expert in those everyday situations, we are creating this so-called, this actually long-term working memory, if you like. We create those everyday kind of situational schemas filled with some of those specific facts from the book, and we keep this, what is happening in the book at that moment in form of that long-term working memory for that specific situation, for that specific reading, for that specific task, reading task, if you like. So that is example of that long-term working memory for that kind of common kind of activity. But in every other area of expertise, experts form this type of long-term working memories for a specific task. That's how they perform efficiently, because they have combined all these activated schemas from long-term memory together with a specific element of the task in one of that kind of one construct. Experts able to have many schema automated. They don't consciously do many simple or lower level procedures, and they do them automatically. Like in mathematics, all these simple lower level calculations, they are done automatically, so the experts focus more on more higher level kind of part of the task. So that allows also to save this working memory capacity and reduce demand because they have automated schemas. So, and finally, the expert walk forward, not backwards. You remember in that mean sense analysis that I example in this triangle, the task in geometry? You walk backwards from the goal, trying to get back to your current position and reduce that distance. That's pretty much novice approach, that heuristics that novices use when they don't have schemas. The experts actually walk forward, not backwards. They walk from the current position, they activate the schema for that situation, and they do the move. forward, like those chess players. They see the board configuration, they activate the chunks or schema for that specific situation, and they do the move, the forward move. They don't reasoning from the some goal winning kind of position and then trying to get back to a lot of reasoning. So experts don't do much of reasoning really. They recall schemas and apply those schemas. So reasoning is a part of this more like problem search, which is a characteristic of novice problem solving. All right, so what is implication for improving problem solving, for learning problem solving, in this case from these facts about of that knowledge of expert problem solving? So firstly is, of course, acquisition of extensive domain-specific knowledge is important. That's the way to be good in problem solving. That's actually what, from my recollection, what helped me to be good in those mathematical competitions, acquiring a lot of those domain-specific solution procedures for specific tasks, rather than studying and trying to apply these general problem-solving methods. So in everyday situation, when you have a broken car on the road, you call a mechanic to come and fix it quickly. You don't call any general problem solving, anyone who good general in problem solving, because they might potentially solve it in a few hours or days, but take a lot of time. You call the mechanic comes, sees the situation, activates the schemas that they already have for this specific situation, categorize the situation accordingly, and come up with solution immediately, almost immediately, or quickly at least, and solve the problem. So teaching those general heuristics like trial and error or mean sense analysis or any other general heuristics, teaching them is pretty much useless exercise and wasting of time. Firstly, because they are not really efficient in problem solving, but for other reasons, because most of them are actually biologically primary in nature. And we know from the previous discussion that biologically primary type of knowledge or skills is something that not really need to be taught intentionally. The people acquire them by being involved into some environment here as any biologically primary knowledge. So random search problem, random kind of problem search, this generating random solution and checking them and trialing them, and that all the things that normally the people do based on this intuitive biologically primary knowledge that we're predisposed to acquire and use actually intuitively, rapidly, and without much of specific instruction in educational institution. Therefore, from this perspective, I know there is some even courses in problem solving that trying to essentially base on teaching people how to use these general problem solving heuristics like mean sense analysis or trial and error or anything similar. And from this perspective, it's not very effective way of improving problem solving really. So you become expert problem solving in a specific area, not in every area. So you need to acquire those specific domain-specific schemas. Domain-specific meaning specific procedure, but also some of those general domain-specific knowledge, like principles and more kind of general knowledge within a domain. But that would be still specific task area. So studying expert solutions would be helpful in this, of course, because you will see how expert categorize problem, because the categorization is especially important to emphasize here, how expert categorize problem, like in those physics and those kind of example. Because if you categorize this correctly, if you categorize it according to the principles, to the general schemas in a field, you will be able to come up with solution accordingly. So studying those expert solutions important. Other thing is extended engagement in the domain. So if you studied it for a short period of time and hoping to become an expert is again probably not much expectation here. You have to be engaged in this specific domain for quite a substantial amount of time to become good in problem solving in that specific domain. So also it's important to not to kind of again some randomly approach that domain and then study one piece of knowledge here, one piece of there, or one schema here. You have to identify some kind of that core set of schemas in that specific domain that would allow you to become an expert. Those key set of chunks, if you like, that most important in that specific domain, and focus in instruction or learning on those specific type of schemas. So it doesn't only, that kind of recommendation generally comes from all those studies of expertise like Erickson and other who studies like expert performance, but they apply also to the school level, if you like, performance as well, because we can talk about expertise in that narrow sense, not professional expertise, of course, but for example, expertise in some specific mathematics school task area, like solving some linear equation. Someone could become expert in solving sort of linear equation in school mathematics. We still could talk about some expertise in narrow sense in this area, and therefore all those recommendations pretty much would be applicable here too. So identifying those schemas in the task domain essentially lead us to, we can talk about schema-based instruction, if you like. So we identify the essential set of schemas in a specific task area, and we teach students that set of schemas, that set of categorization of life, if you like, in that specific task area, hoping that they will become more good problem solving in that specific area. For example, in arithmetic word problems, there was many different studies, and yeah, probably people in this school, in this audience, they familiar with some of those studies, definitely. So I'm not anything kind of revealing here that schema-based instruction in arithmetic word problems by Sandra Marshall was the book was written about the whole thing. And there are many similar attempts of identifying those schemas in this area, specifically published as well, because it's notoriously difficult area for students in that sort of middle of the high primary kind of level, because they contain all of the kind of text, everyday situations, and come up with solution. So what they did, they identified some type of schemas. They described some type of possible schemas or situations as a base for the categorization of those situations. So, for example, this situation, or similar to that one, where there is with a basket with fruit and with apples and oranges or anything else, or passengers on a bus, but that generally some kind of change situation would be defined as a change schema. So in this situation, you need to use this type of specific operation. So in this case, you need to do some kind of deduction, right? So in some other situation, you need to do some addition and so on. So you need to apply specific arithmetic sort of operation for that type of situation. Similarly for this group schema, that kind of group, when you have several objects that contains a group. So again, those elements are linked in a specific way to form this group, and the situation, that the specific situation, which is also implies some specific move to do in this type. Some others, and so on. So I don't list all of them. There is some 5 or so those kind of type of schemas identified, and then students will get familiar with those different type of situation and what they have to do in each of those situations, and the instruction was based on this. So that the screenshot from that computer screen that was was implemented. As you see, those 5 types of schemas, they were diagrammatically represented in so like this change schema, as you see now in the middle, and here actually presented. This type of schema, for each type of schema, was also diagrammatically represented in a specific way. So the students got familiar with situation, their diagrammatic representations, and specific moves. So in each more complex task, they can single out, sometimes could be not one, but several of those schemas sequentially applied. But for each of those, they could not already move. So that makes the solution much more easier, consistent, and effective, if you like, right? Because it's not would be any random or quasi-random. That would be something based on a specific knowledge, and in this kind of forward way, you identify the schema and you apply the move according to that schema. So that hopefully will help to solve the problem. That's kind of another example from some web application. Again, trying to help students to manage those arithmetic word problems. Similar way, categorizing those situations into some schemas, associating them with some diagrammatic representations, and basing on the teaching on this. So the schema-based instruction, right? So that's one thing that in terms of improving problem solving based on this knowledge of expert performance. Another one relates to the deliberate practice. One of the things mentioned in one of the previous schemes was that kind of engagement, significant engagement in a domain is important. No, not just some occasional studies and so on. You have to consistently be engaged in the domain to become good problem solving. So Erickson in the study suggested this kind of deliberate practice idea for improving this training in to help people to become good problem solving or expert in a specific field. So this kind of deliberate practice is not just some regular practice that we normally use, some just repeatedly doing some exercises in some area. What they emphasize here, 2 things. Firstly, you need to practice especially in your weak area, not in the area where you're already good. And secondly, you always have to do this to have some expert feedback from whether expert instructor or some software that built for this, but which would correct you if you do the wrong. So you not kind of automate those kind of wrong solutions. So you have this feedback permanently. So weak areas and feedback, 2 important things of what is deliberate practice is about. So it means extensive kind of practice. So therefore, it could be not motivating in itself because it's a lot of effort training to trying to repeatedly do this kind of problem solving in the same area, and especially in your weak areas that you're not kind of very good, but you force yourself to do that. So it's but not it's self-motivating, but motivation obviously comes from reaching higher level of performance in this case that you hope and achieve in the end. So that's the problem, but that most of us when we learning something, when we get into the level that we see that we can solve the problem, and at that stage we just stop it, because that kind of acceptable level we more or less know how to solve the problem, and then stop, we go to the other things. What is important here is that even and you think you know how to solve problems, it's important to do all that deliberately and practice more and more in those especially weak areas when you're still not perfect, and refining that with feedback. So that mode of deliberate practice. So talking about the deliberate practice, of course, in these studies of Erickson on expertise, they found that they could account that deliberate practice could account for significant actually differences in expert performance, even among the experts after who actually have the significant practice in some specific area already. So the amount of the deliberate practice could account for differences between them. So even total, all of them, let's say, group the practice a lot, but those who practice in this kind of form of deliberate practice for the same amount of time, essentially, it could perform as those studies showed would perform, would expect it to perform better. So, so the more practice, the deliberate practice, the better one gets. So, some people could have some abilities, some talent to specific, some aptitude to specific area, but if you don't practice it, and you can essentially let people say use it or lose it. Whether you practice and get improved, or you can lose that initial benefits you can might in some specific area. So therefore, the more deliberate practice, the earlier the start of that deliberate practice could also have some important implications. The age of starting, therefore, we have many examples when those the people in some area of expertise, like those in music, most notoriously, those some children that stay playing in very early age, and therefore they're able to accumulate a much more kind of amount of time of that deliberate practice, and therefore become better. Even some few years would make a difference in this case. So that's important for that reason as well. So whatever the initial kind of level of abilities or talents that could help you develop faster, but if it's not supplemented with this kind of effort and deliberate kind of practice, that could be suddenly this kind of be lost in some way. So that kind of about the deliberate practice and implications from study in expertise, implication for improving problem solving abilities and skills. So next questions that we need to cover, as was mentioned, as I talk about in the beginning, is a problem solving and an instructional method. So would the problem solving, engaging in problem solving itself without anything else would be good as problem solving learning means. So here we have some interesting kind of facts or results from cognitive load actually area, from some set of studies that from which cognitive load theory actually started. So what happens initially in the early 80s, the John Svela who developed the cognitive load theory, he was working not in any instructional really area. He was trained psychologist, and he was studying at that time purely psychological kind of research, doing psychological research, just studying how people kind of solve problems in that kind of purely in areas that many psychologists actually use. Some not really instructionally relevant area, like some of those puzzle problems or some kind of artificially created kind of task. No, not a realistic instructional task, like those puzzle problems. Some puzzles, those whatever it is, some labyrinths or similar kind of puzzles. So what they discovered, some of those problems can very clearly available solution strategies. If you apply it, you will get the solution very quickly. But if you don't know it, obviously you do this kind of training, random trial and error and so on, this random problem search. So what happened? The people who didn't know the strategies, they do this random problem search again and again. They, at some stage, come out with solution. They reach the goal. The next time, with the same problem, they again continue to do this random problem search, rather than applying some of that kind of strategies that is available that get them quick result. So, like in that a linear equation, trial and error, that I demonstrated, use some trial and error approach when students substitute for x. That was actually example taken from actual experience in school when we did this in some stage. The students was able to solve, like, it was 20 tasks in that test. All 20 were solved successfully, 100%. But up to the very end, it continued to do this trial and error, even though solution procedure very quickly divide the right-hand side on then coefficient, and you got the answer. Still, 20 tasks later, the student continued doing this trial and error again and again and again, coming out with correct solution, but still doing the same. The same happened here. So that was kind of phenomena. Why is that happening? Why is it people didn't learn? That was a question they asked here. Why they did a lot of these trial and error attempts, even solved the problem successfully, but didn't learn a solution, a schema that would solve this problem quickly and efficiently. They continued to do this trial and error again and again without learning. So the same was repeated in mathematics and science problem in similar situation, similar to what I said. They come up with solution but didn't learn. So the answer eventually was found when they analyzed this kind of nature of this random problem solving. Using this means ends analysis or any other this random problem search would actually involve a lot of information to be processed at the same time. Look at this means ends analysis. You have to be able to keep a lot of information in your working memory. You have to keep that the goal of the problem. You have to keep your current state. You have to keep those sub-goal, another one, another one that you come up, because later you have to fit how to go from that sub-goal to another kind of sub-goal. So you have to keep a lot of that information in your working memory when you're doing this. Even when you're doing this trial and error, you have to keep your what the value of that x get you closer, which would be next that get you even more closer to that right-hand sort of number, and keep them in your mind, in your working memory in between. So that would impose a heavy working memory load on those novice learners in this case. They're novice because they didn't know the schema in this area, right? So the answer to this question is that those problem solving by using those search methods, those heuristics, always produce heavy working memory load, therefore leaving no actual resources or working memory resources or cognitive resources for constructing, for actually even seeing those solution procedures, those schemas, those solution procedures that could take you from the solution very quickly from the initial state. So this problem solving by mean sense analysis or other these problem search method are generated heavy cognitive load, which is in this case extraneous really cognitive load, because it's not directly related to learning schema. You are doing a lot of those search procedures and trial and error attempts, which is not really directly related to learning. You learn nothing from that specific experience. You can come up with solution, but you don't learn the solution effective solution schema from that. So therefore, what the conclusion was from all those studies, that the conventional problem solving, essentially, that meaning that using this heuristic for novice learners, just giving them many problems to solve in the absence of knowledge and without presenting actually that knowledge, would be not really efficient way of teaching problem solving method or efficient instructional method. So we need to we need to reduce this extraneous cognitive load that embedded, that is present in this random problem solving processes by search. So how we can do that? So the next, that would be, we will be talking about today, and to some degree the next lecture, how we can reduce that extraneous cognitive load in problem solving, in teaching actually problem solving. So one way that was suggested is if the main culprit actually in this, that imposing this heavy cognitive load, that goal that you have to keep in your mind when you solving problems by these methods, and you trying to get closer to that goal, and you invent some sub goals, and you have to keep that initial state as well. So, but everything is directed to that kind of problem goal. So it looks like that problem goal, the presence of that problem goal that you need to achieve, is something that critical in creating all this working memory load around this search and all those steps that you do to achieve that goal. So in this case, facilitating problem solving could possibly be achieved by somehow removing that problem goal. So not to have it all time in front of you, because that creates cognitive load, but refocusing your direction to some specific problem states that you normally have it on a way to that goal, and to associated moves with that problem states. So what if we redefine the problem in a way that the goal is not explicitly presented? So in specific goal, sometimes it's called, defining the in specific goal, or using these so-called goal-free problems, what was suggested. So what goal-free problem is that, for example, in that geometry task that was find angle x, you remember was there, ABC. What we formulate the task, find the values as many angles as possible. Not the specific angle, but the task is find the value of as many angles as possible. In general case, could be, instead of finding some value of parameter x, whatever the task is, you can reformulate the problem like in this goal-free way, calculate the values of as many parameters as you can in this situation, in this task area. So again, some empirical evidence with this goal-free, was called goal-free effect. They found that the students who absolutely in the same environment, but a two experimental group, ones that have this goal present, they continue to use this search method essentially again and again, like with those puzzles. With goal-free problems, actually what happens that the students who were presented with those goal-free problems, actually they switched rapidly to those more forward-walking procedures in post-instruction tests. So they have demonstrated some evidence of acquired schemas. So it's because they were facing with those specific situation, specific task states, problem states, and associated moves. So their working memory was not occupied by a lot more pretty much unnecessary information. All those are goals, the goal, and all those intermediate states, and so on. They were occupied only with a specific task state, problem state, and a specific move for that state. And that essentially produced this goal-free effect. So attention was redirected in this case from the problem goal to those problem states and associated moves that were required for schema acquisition for those specific problem situations, and that define the associated moves. So in this case, we actually walking forward, if you like, not backward from the goal, but we have different possible situation, different possible task problem states, and we're moving forward from each of those problem state forward, applying some specific move. So in a total, that would accumulate with the knowledge of those moves for each of those specific problem situation. So, of course, that goal-free technique was demonstrated in those rather simple mathematics domain, like those linear algebra problem or similar, on these geometry problems. That problems don't have very big the problem space, what is called, many possible intermediate situations, intermediate problem sort of states. So the number of moves was rather limited, and they will be all covered in these goal-free experiences. In cases when we have significant goal, significant problem space, so many possible moves that need to be instructed, that might be not very kind of applicable, because that simply would require a lot of time, a lot of space. So, but for that, we need to come up with some other possible techniques that will improve this problem solving. What technique? Again, that I refer to the next lecture, but we're going to talk about worked examples as an alternative to conventional problem solving. So starting worked example first, and then doing the problem solving, something like that. We're going to talk about worked examples, direct instruction, and other things related to this in the next lecture. But today, just to complete this lecture about problem solving. So, as you see, the problem solving by itself in a pure form, like what we call conventional problem solving, just giving student a lot of problems to solve without much any of initial kind of instruction, without much of example provided initially, but engaging them a lot of problem solving, as you see, doesn't really work as a efficient instructional method because of that working memory overload. But still, question is there any productive role of problem solving in learning generally? Of course there are. The one is the means of that practicing of schema automation and so on. When you provided students with a solution procedure, they learn the solution procedure. They acquired it, and then they need to practice a lot. Partly that deliberate practice, essentially, that also effective role of problem solving. Problem solving is a means of schema automation. So to get to those procedures, some lower level procedures automated, students need to do a lot of problem solving. Of course, that productive role of problem solving, but that's something like the problem solving following already acquisition of at least knowledge about solution procedures, and then we do the problem solving and automate it. That one role, and that obvious one, which was obvious always for is not a revelation, of course. The problem solving, we know that to become good, you need to practice a lot in problem solving. But another could be also problem solving. We talk until now about problem solving as a way of learning solution schemas, or as a way of instructing in solution prima. That's the primary goal, the important goal, the most important one in instruction, but not the only one. The problem solving could be also the means of achieving some other instructional goals, which could not be the immediate goal in some instructional situation at the moment. Acquiring solution schema could be something else, like, for example, motivation or engaging learners. You can present some problems, some interesting problems to engage learners or motivate them. That could be one possible way of using problem solving right from the beginning, or activating their prior knowledge. They facing the new problem, they might be able to see what they know relevant to this problem or not, and in this way activate prior knowledge. Some establish their knowledge gaps and so on. So could be some other instructional goals that the problem solving could be useful to achieving those goals right from the beginning without even kind of any initial acquisition of problem-solving solution or procedures. So from this point of view, I return back to that lecture 1 when I talk about this motivation, role of motivation in cognition, and we discuss this possibility maybe to add some additional principle to those natural information processing system in case of human cognition and a level of intelligent natural information processing system. There is some indication, at least for me, that it's possible, and we need some additional principle that would cover in this case this deliberate, intentional processing of information in working memory, how we acquire secondary knowledge. So whether it would be called, as I suggested, an intention to act, preparedness for learners. In the end, I decided that the intention to learn possibly would be that sort of principle, a good name, but that intention to learn, meaning the intention to engage in conscious processing of information in working memory, deliberate processing, intentional processing information, secondary information in working memory, in terms of developing the secondary knowledge and adapting to environment in this case. So, but that secondary knowledge acquisition need motivation. We're not primarily evolutionary predisposed to be motivated to acquisition of secondary knowledge, that knowledge of science or anything else that we need in school. We need some motivation for that. That intention to learn in a working memory, that's something that defines that we need to be motivated for that intention. So this principle essentially will cover that kind of relation between cognition and motivation from this point of view, and problem solving in this case, and the means of implementing this principle could be, in this case, serve that another productive role of problem solving as a way of of implementing essentially that principle. So, some studies, again, next lecture I will talk a little bit about that, actually provided some empirical evidence for this, like with some productive failure approaches, invention by learning by invention, and so on. They indicated that initial problem solving without even direct instruction first, but then followed by direct instruction. But still, direct instruction preceded by problem solving could have some role in achieving some specific instructional goals, like those goals that I just mentioned, including some motivation, that would include some potentially another productive role of problem solving in that conventional role, problem solving as a search, not problem solving as a applying already available schemas or knowledge like experts do. So that's pretty much what I wanted to say today. So the next lecture, the final one, would be essentially about building knowledge based in long-term memory. And we're going to talk about worked example effect in cognitive load theory as an instructional alternative to that conventional problem search-based method. We talk about sequencing of explicit instruction and problem solving, so selecting in optimal sequences. And we're going to talk about these specific instructional goals as a major determinant of instructional means. So what kind of means we're going to use in specific situation, whether it's worked example, whether it's problem solving or anything else, determined to significant degree by specific instructional goal that need to be achieved in that specific situation, instructional situation, not general, but in specific situation of specific learning task. So that's pretty much all for today, and thank you for attention, and if any questions, I'll try to answer.
Thank you. So any questions from the room? Okay.
Well, it's not really a weird question, but and people that are talented and people that are really practicing hard and working hard. So I have always wanted, especially in sports, I think you can see that you have really talented people, but they sometimes are outperformed by people that are not so talented, but they have really practiced a lot and worked hard. And I always wonder how this happens, because being really talented is the optimal precondition. And I would always think these people would be especially motivated to then practice even harder, because then they would be unstoppable. But this hardly happens. So I'm always wondering why they can be outperformed by people who are not that talented, but really are determined to work hard and to practice a lot and to basically be better. So I'm just like, or are people that are really talented less motivated because they know that they are really good? I don't know.
Yeah.
I'm always wondering why it is like that.
But that studies, it mostly was conducted by Ericsson and his group, by late Ericsson, and he conducted a lot of studies, specifically in different areas of sport.
Yeah.
So how the highest level of expertise and high levels of proficiency in some specific type of sports could be achieved. And they have a lot of evidence that this deliberate practice, this kind of what they suggested, and a lot of argument, and that could be really helpful in that. So that's, I didn't do any specific research myself in that. I just I just included this Ericsson's result, some very brief overview here, just to show this role of deliberate practice. What we did actually in myself with some students, we actually use this deliberate practice regime in mathematics with that specific task in mathematics, in like it was year 7 or year 8 or something like that, with some very specific task. So, and it showed that this type of approach actually worked in secondary school mathematics. So when you do this deliberate practice with those two, practicing in weak areas and having this feedback continuously all the time, and that was an efficient way to improve performance in this. Of course, it's not sport, but I agree with you. But nothing I can add really, but other than to some degree, this research can explain that phenomena. Yes, that people motivated by the perspective of achieving top level of performance in the field, that level of motivation can get them ahead of someone who has maybe some specific ability and achieve some previous result, but somehow that is this delivery practice regime or some practice generally. So again, that use it or lose it. That was the conclusion here.
So, because I'm always wondering, I mean, people that are like extremely talented, obviously they are so much ahead of everyone else in this specific field, but then you can always see that that it doesn't matter that much, because somebody who is really determined to be better and to practice, and he for sure might be outperformed this talented person. So I'm always wondering if talent is overrated completely, because you can outperform that person if you just are determined to do so, you know. And you can see that everywhere in sports and in whatever kind of field, you know. So I'm always like,
yeah, I wouldn't say that talent is overrated. It's just kind of okay. You can reach the level more or less you have with no effort.
yeah.
So I
That's
wouldn't say that it's like
it's so overrated. Yeah. Why
Are they less?
yeah, I wouldn't say that it's overrated.
Are they less
You would not
motivated
say
or something?
Yeah, because like it's kind of like from the perspective of the person, it's like yeah, well, like like if the two compensate each other, then I wouldn't say one of these is overrated. Yeah, well, of course you can kind of yeah compensate for, but this happens at like massive costs, like other areas of your life to I don't know like other aspects that you need to put this work in. So yeah, I don't. Yeah, well.
I think in the general public it's overestimated.
Yeah.
Absolutely, I think that's the
Me
case.
too, actually. Because I don't know. I mean, I'm not sure if I could be that determined. Like, you see it in so many cases that sometimes talent basically doesn't mean anything.
Or we can say it in the opposite way, why more people are more motivated than talented people.
Because the talented one exists, or they are the motivator.
Maybe, first of all, I do believe that talent and motivation are not always linked. So there's no correlation in between. So instead of saying why talented people they are not, some not so talented people are so motivated. So why you think that you got this motivation, you can do something even though you are not talented? This is the thing that we want to do to our students. I don't think most of our students.
I think we also have some comment from online. Yes. So Adam, what's your comment, Adam?
Hi, how nice to
Look,
see you. Slava, thank you.
I don't have anything to add to that discussion because pretty much, yeah, it's whatever we can cover.
Sorry.
Can you hear me, Ohio?
Maybe the loudness of the computer.
Okay, what did it do?
Hold on 1 second. Can you say something now?
Hi, can you hear me?
Yes, it's getting better. Yeah.
That's great. Nice to see you, Ohio, and Slava. Thank you so much for a wonderful lecture. It's Adam Shalevsky from Canada. I couldn't hear the whole discussion in the room, but I was able to make out that you're talking a bit about talent, and I think one of the audience members mentioned that talent might be a bit overrated. In fact, there's a book called "Talent is Overrated," and it's a fascinating read, and perhaps some of you in the audience have read it. I think Erickson would argue that talent is very much overrated. He does describe in one of his books a study that was done, I believe it was in Japan, about perfect pitch. And perfect pitch, of course, is one of these ideas where has always traditionally been thought that some individuals have the capacity to have perfect pitch in music and others don't. And that was always thought to be a talent-based phenomenon. And what they found is that that the base rate for perfect pitch was X. I don't remember what that was. But then they took a group of young students and they put them in a music school from a very young age. And they were able to find that if trained properly with deliberate practice, they were able to accomplish a perfect pitch rate in that population of something like 20 times the base rate in the population that would have been expected. All that to say that I think probably based on that study, based on a lot of Erickson's work, I think talent is probably a bit of a misconception. I think there's probably a lot of motivation that goes along with talent, but in my humble view, I think that it probably is quite overrated, and deliberate practice is really where it's at. There's certainly some natural phenomena that happen in athletics, for example, in sports. Someone's height, their muscle mass, those are things that are hard to change overall. Certainly IQ and intelligence to some degree is probably also more of a static idea. But most other domain-specific, what we call talents in quotation marks, I think probably have less of an impact than we think. Just my thoughts.
Thank you very much. That's like more like a comment than the questions, and I agree. I appreciate. Look, my purpose not was to discuss the talent as such in this lecture. It's more about instruction, how more efficiently teach problem solving. So deliberate practice, that was my kind of intention to at least to focus attention on that, on deliberate practice as an instructional kind of method, right? Instructional way to improve problem solving. Speaking about the talent and all this balancing talent and instruction is well above this topic of this lecture, but that interesting discussion here, and thank you thank you very much for your comment. That's kind of definitely relevant and apt.
Yeah, thank you, Slava. And I guess my comment was less directed at the lecture and more about the conversation I overheard in the room. And again, it's hard when you're online.
Yeah.
But it was. I just thought I'd just add to that a little bit. I have another. Do you mind if I ask you another question about some of your work?
Yes.
I wasn't able to attend your previous lecture when you probably talked a bit more about expertise reversal, and I've read a lot of your work on expertise reversal. Do you think that's so? I believe the way that you describe it is more from an educational perspective. Do you think there are? Do you think we can extend that work to performance as well? Because what I found is not only do experts learn worse with instructional methods that are developed for novices, but also that their performance is worse when they're examined with strategies that are used to examine novices. And I think I don't think that's exactly what you meant when you talk about expertise reversal, but it's something that I've been thinking about, and I wonder if you have any comments about that. My specific kind of example is about physicians who are examined in simulated settings, and how we find that experts, not only do they learn, they don't learn quite as well in simulation, they also perform worse because the environment isn't, the fidelity isn't there based on, the fidelity that they're used to. Curious to hear your thoughts.
Okay, yeah, look, a good question. But firstly, I didn't talk much about expertise reversal as such yet, because in this series of lectures, it's still upcoming. It would be first lecture in the next series would be specific of expertise reversal. It happens sometimes next year in May, wherever I can get back to continue my visit here. Secondly, definitely that could be extended to performance, and if you want some specific, I wouldn't be able to talk about that much now, but there is a paper that we've written together with Fred Paas and Rickes, another in 2012. It's actually about expertise reversal effect in general, with extension to other areas. It's covered, so you can find it. It's Kalyuga, Paas, and Rickes, or Kalyuga, Rickes, and Paas again in that sequence. 2012 in Educational Psychology Review. That paper covered that specific issue to a good degree. Actually, the similar phenomena was found not only in this kind of educational area, but for example, again, we return into that sport area, in sports area, and even in other areas. For example, this so-called choking effect, when an expert, sometimes who are performing something very well, excellent level, and then they come to some examination commission or something, and they ask to demonstrate that or describe that, and then what got chocked, and that they not able to perform to up to their level of how they usually perform. They put into this environment of the specific, they were requested to perform, and they actually not able to demonstrate that. That's just one example of those. Another one, when they in sports again, there was some studies in I guess in golf and specifically, they show that when the trainers try to explain these movements in details, that in some of those physical specific movements explained in details that pretty much work well for novices when they explain to them. And when they try to improve the performance of experts who already actually mastered that kind of move to significant degree of perfection, this instruction essentially do the reverse, actually, rather than helpful, but reverse, because those experts have to significant degree sort of to do some reverse engineering, if you like. They already automated skill, but in this case they have to go back to the state where they were learning it, and this integrates these kind of skills in those partial parts that they learn, and that process would essentially make performance worse. So similar phenomena to this. So different sort of examples. I'm not able now to quickly on a flight actually to recall all of them. Intermediate, another intermediate so-called defect is called in medical training, when there is some situations where mediums of level students, the expert perform worse in some specific situation when some are graduating kind of medical students on some, because again some of this type of interference happening. So some detailed instruction could have some interference effect with the performance in many areas, in sport, in some professional training, in other areas. So we categorize these examples like some broadly like expertise reversal effect in general, not only in this kind of academic instruction area, academic learning, but generally in professional performance as well. So all of those kind of exemplifies those expertise reversal effect as a phenomena much broader than the applicable to academic learning that we're discussing in these kind of lectures. So, but again, for details, you can look at that paper, and that you get some possibly interesting information.
Thank you very much. I just found the paper, and I've been following your work for years, so it's great to see you online. Thank you so much.
Thank you, Adam. So any other questions? Okay, so if no questions, so Slava will have the last lecture on 15th, so late Thursday, from 11 to 1 p.m. Okay. Thank you, everyone, and also thank you people online.
Thank you.
Bye bye. See you on Thursday.